Hi, my name is Shelemia Nyamuryekung'e, a research associate working under the Department of Animal and Range Sciences, New Mexico State University. And today I'll be talking about precision ranching, which is one of the projects that is covered under the Sustainable Southwest Beef Project. For the roadmap, I'll start by talking about Sustainable Southwest Beef Project overall, and then dig deep into the precision ranching, which is my presentation today. Then I'll look at the implementation of precision ranching, looking at case studies that our lab has conducted, where we will be looking at different sensors that can apply to precision ranching, the infrastructure needed, and the application of precision ranching looking at a cow-calf scenario. And I will end with the future of precision ranching by posing challenges and opportunities associated with it. The Sustainable Southwest Beef Project, I'd like to orient you to a publication by Spiegel and others that have gone in depth reviewing the different components of the project. But as for a summary, I'll read the mission statement, which states, the Sustainable Southwest Beef team is evaluating LoRa Criollo cattle, precision technology, and trade-offs among the beef supply chain options, from pasture to plate to enhance range and rangeland resilience in the Southwest United States. This is a 5-year CAP grant by the United States Department of Agriculture, NIFA grant. And the strategies that were mentioned in the mission statement include the heritage cattle breed genetic study, which is also depicted at the top of the diagram here, the precision ranching, which I'll be talking about in the red box, and the alternative supply chain, which I believe will be discussed in next presentations. Under the precision agriculture system, I've included a simple diagram here, looking at input, processing, and output. So on the precision agriculture, on input we'll be looking at sensors, and an output will be an agricultural equipment either being activated or deactivated. So for a simple example, let's say a poultry production system where an input will be temperature loggers, a processing center will be a set maximum or minimum temperature, and an associated output will be a ventilation being enabled or on, or a ventilation being disabled. However, the complexity of precision agriculture will be associated with the number of input and the number of output associated with the processing center. For instance, the example that I've just given about the poultry farming, it will be classified as a single input, single output. And it's very common in most of the intensive agriculture and crop science. In an extensive system, we're probably going to be looking at multiple inputs and multiple output scenarios. For instance, in range management, not only are we going to be looking at the animal, but we're also going to associate its environment, which will also have to be feeding information through sensors. As explored by LACA 2009, precision livestock production focuses on individual components and exploits heterogeneity of space and among individual animals, improving efficiency and sustainability. In their model, they looked at sensors gathering information from individual cow, but also the environment, and relying it to a decision support center, where in turn it would control feeders, gates, or visual stimuli to the animal to move to a designated area. However, in their example, they have shown a fully automation of precision grazing system. But in our proposed work, we are looking at a scenario where precision agriculture helps the existing ranch manager in monitoring or giving alerts when needed for the ranch manager to take decisive actions. In this example, it also shows the importance of data in precision agriculture. So for the following slides, we will be talking about different mechanisms that could enable data transmission in an extensive system to enable the precision agriculture to be more fluid. Under the implementation of precision ranching, the biggest hurdle was to find the right communication platform. For this project, we chose LoRaWAN, which stands for Long Range Wide Area Network, and a good lead review has been done by Sanchez 2018 that I've cited on my introduction here, but also the application of this system on real-time management in extensive livestock system has been done by Waterhouse 2019. The depiction presented here is borrowed from Actility, showing how the data moves through this system. On the first box, we have the sensory devices, which for our example here, it's an Abiway tracker, which I will explain in the next slide about sensors, but will be conveying GPS locations. On the second box, we are looking at the infrastructure itself with LoRaWAN gateway, where the Abiway trackers will be able to transfer their data to these LoRaWAN gateways. The LoRaWAN gateways will relay that information to a cloud system. And from that cloud system, an application setup would download that data and manage it to give out information that could be used by the rancher. So a simple way of explaining this model here is that the LoRa system or the LoRa gateway could be viewed as you buying a mobile phone, and whereas the network server or the data manager will be like you subscribing the phone to either Verizon or AT&T and so forth. So those are your data management platforms. And here, what we are looking at is Actility. And then from the data management, you need an application software where it would make use of that data. So it's the application platform where on a phone example, as I have stated, will be like you downloading a software from the Apple Store. And that software now will make use of the data that has been acquired from the trackers with this example. So for the following slides, I will be looking at the sensory devices. I'll be looking at the infrastructure by a case study that we have done and the application of this LoRa system at our research centers. Under sensory devices, telemetry technology has been a known platform in animal science or agriculture. For instance, in dairy industry, jaw movement, acoustic monitoring, heart rate, core temperature, body condition score evaluated by images, or remote weighing are some of a few mechanisms that have been advanced within that industry. A good publication evaluating all the telemetry technology that could be used on an animal will be with Halachimi in 2019 by showing you the depiction of one of the figures in the publication. The thing is, with engineers, they're saying that as long as you're having a telemetry device, you can enable it to become a LoRa LoRaWAN enabled by just installing a simple chip in the circuit of that telemetry device. But for this project, we wanted to look at existing technology that is off the shelf that could help in this precision agriculture ranching platform. For those reasons, we settled by using an RB tracker that will give us animal position and location. For this experiment, we will be conducting data from an industrial tracker, but the company has just put out a compact tracker which shows promising capabilities as a device to be used in precision livestock production. So for instance, on a table down here, I'm showing that both models, the industrial and compact tracker, are LoRaWAN enabled, and they both have minimum capabilities of any GPS trackers by collecting GPS positions. They have an accelerometer and temperature data loggers. But a compact tracker, which is a newer model and is the black one on this image next here, has a capability of showing a proximity resolution, meaning that two compact trackers could be associated with a distance from each other. And I will show their importance when I'm looking at the cow-calf data. Also, the newer model gives us an easier access to battery, which is another important topic to discuss about precision agriculture with battery limitation. And the follow-up is also for these trackers, even though they were designed for asset tracking, to have an accessory that could be incorporated with these trackers to be fitted into the livestock industry. And both of these trackers do not have that accessory, but I believe with time, this company might be developing or getting a side company to access that market. The concern about the battery is not a new problem in telemetry equipment. Even an onboard platform of GPS collars, battery has always been a concern, where it limits either for an experimental design, you have to either limit the duration of that experiment by taking GPS position at frequent intervals, or space out the GPS position frequency and therefore gaining a more battery life in so doing. So for our sake to solve that, we looked at incorporating both the GPS data and the accelerometer data, whereas the accelerometer data were collected at more frequent intervals, and due to the fact that they are using low battery power compared to the GPS data acquisition. And with the GPS data acquisition, we put it at a spaced interval. And by doing that, we lose the accuracy of GPS being able to give us inference of animal behavior, but will give us a good platform of spatial analysis. For instance, to overall know where the cow is at. You can calculate a daily distance traveled by that cow, but you will not be able to discriminate certain activities within a huge spaced out GPS positions. So for the animal behavioral spectrum, we moved into using the accelerometer, which for our study were collected at 1 minute interval to be able to give us an inference of the animal's behavioral spectrum. Communication infrastructure is probably the most important platform in enabling precision agriculture. And this is because in most rural settings, either cell phone coverage or internet access has a very poor coverage. For this example, we are looking at the Clayton Livestock Research Center, New Mexico, where we deployed a LoRa gateway probably just a few weeks ago. And in doing so, I'll take you through all the steps that need to be considered when setting a LoRa system on a ranch. So on the right, or it might be your left, I do not know how the screen will be oriented to you, is a simple diagram of the LoRa setup, which includes an antenna, the LoRa gateway itself, and then we have power over Ethernet cable running. And then in this box, there needs to be a power outlet, and also where the information or data that has been received through the antenna will be pushed into the cloud system or the data management system platform through the internet router. Now, as I have already mentioned earlier, in rural setting, internet connectivity or cell phone coverage could be a problem, and therefore troubleshooting how we're going to push that data from the gateway is something that is case dependent. For instance, there are some gateways out there that have a capability of having a 4G SIM card, and therefore would push the data straight into a cellular kind of communication. But also if it is a complete isolated location on the internet router platform, we could put a backhaul device which will be propagating the data from one tower to the next to an end place where the data will be able to be pushed into the internet access. On the power supply area, it is also very flexible. We have already managed to use, for instance, a solar power instead of just an electrical outlet to be able to use the LoRa system in situations where power is not available. Now, on the implementation of looking for a position for the LoRa gateway, we looked at different positions as candidate locations. For instance, in our map here, the green shows places where there's only tower, where the red shows tower and power, and yellow shows tower, power, and Wi-Fi access. And one of the yellow spots that we have chosen was also having a height advantage. It was at the feed mill tower, as you can see on figure 2, and its height was around 80 feet. On the next slide, I will emphasize on the height placement of the antenna, and it is directly correlated with the coverage range that you will get from these LoRa devices. But just for a little illustration, is that if you put it at around 30 feet height, which is probably your normal telephone tower height, your coverage will probably be in a minimum of 5 kilometers. But experiments done, for instance, in Spain, where they used the height advantage, they showed a coverage where it could be propagated to almost 20 kilometers. So one of the mechanisms in implementing the infrastructure is first is first noting down candidate locations, but also there is a model that could be run that I will show on the next slide that will give you a better depiction of the coverage of your LoRa system on that chosen location. Under the theoretical LoRa gateway coverage, it is a model that incorporates topography of an area with description of how high your antenna is, and it will show the propagation of your communication in distance locations. So to orient you, on the left, we have New Mexico, and it shows you where Clayton Research Center is at by the red arrow. And on the right side, it is a map showing our LoRa coverage with the distance of 25 meters of height. And just for a distance illustration here, it shows a coverage of around 10 kilometers. And all the painted areas are areas that data can be transmitted, with the light blue showing 100% data transmission, whereas the red, it shows that data could be transmitted, but there could be some other properties that need to be considered, like the vegetation type in those areas and so forth, that could affect your data transmission. But in our Clayton example, our research site was covered with the light blue showing a full coverage of the LoRa system in that model. So this model was rerun with a different height of the antenna, and the coverage had changed tremendously, just considering half of a distance height for the antenna placement. So this just brings up the emphasis on when choosing a location for the antenna or the LoRa gateway, height should be always considered as an advantage to the LoRa system to improve its coverage. But the LoRa gateway device itself has an internal configuration that could improve the coverage of these device by changing its propagation properties or the data rate transmission characteristics as well. Now that throughout the previous slides, I have emphasized on data transmission, and now that we have the data in the cloud, the following slides will show the application of that data in models that could help a rancher facilitate his or her daily activities. For the examples of the application platform, I am considering different stages of a cow-calf operation. When a cow is dry with the non-nursing phase, when a cow is going through paturation, and when a cow is associated with its calf. Under the first scenario, which will probably be the majority of the time, where the cow is without its calf, a non-nursing cow, threshold values are extremely important. What I mean by threshold values are these mean values that are associated with normal behavior. The figure on the left represents accelerometer data that was acquired during August from one cow. And here we are just looking at 1 day activity. And you can see those spikes of the accelerometer concurring with what we are expecting to be the grazing bouts of the cow, as Gregorini illustrates in in his review paper 2012. The following analysis in our data mining will be to now be able to decipher activity budgets using this accelerometer data. For instance, Fogarty et al. 2020 has shown the use of machine learning in order to be able to detect time spent grazing, resting, or traveling, and could help us build up a model of threshold values associated with what we are expecting within a day a cow should be spending time grazing or traveling or resting. And any deviations from that established threshold will be an abnormality and probably will send an alert to a manager to check on that particular cow. For instance, lameness is only second to mastitis in terms of its detrimental effect on herd productivity in dairy cow settings. A good correlation of lameness could be time spent grazing, a reduction in time spent grazing. But also, Tobin and others 2020 used accelerometer as a model of detecting bovine ephemeral fever and were able to successfully detect the onset of the disease 1 day before its clinical diagnosis. These are just examples of how accelerometer readings could help ranch managers facilitate their management of the livestock welfare. But also, the infrequent GPS data could also be used to set threshold values. For instance, distance traveled, area explored, and spatial analysis like times of water visitation within a day could be used to assess normality and abnormality of a cow within the herd. Now that we have emphasized the importance of threshold value, let's look at its application in real setting. Parturition is probably one of the phases in animal production that needs a close management intervention. McIntosh preliminary analysis, who looked at a handful of variables, noted a difference during the calving date. This brings opportunity to precision agriculture with the graph showing a dipping in area explored during calving to be able to accurately assess calving date, but also give a warning to the manager for intervention in order to assist the cow when there is a need to do so. Our last scenario in the application platform is considering a nursing cow. Previous studies done by Nyamuryekung'e and others 2020 have established that cow-calf contact events happen throughout the day. In that study, proximity loggers were used on a pair of a cow and its calf. Even though we did not use LoRa-enabled data acquisition, new compact trackers with the capability of the RFID technology using Bluetooth could enable this data acquisition and analysis. Simpson's preliminary analysis on the data collected by these proximity loggers on the figure on top right showed that this data could be used to detect cow-calf pairing, meaning that ranchers might be able to accurately depict a pedigree of a dam offspring pairing. However, this analysis of pairing dam to a calf was also established with lamb to a ewe proximity analysis by Waterhouse and others in 2019 publication. The last scenario is now, how can precision agriculture help the managers overall? And the simplest application is by managing and locating the animals. By having a real-time location of the animals, managers can cut down time in tracking where their cows are at in these extensive pastures. But other sensors like rain gauge, automated LoRa-enabled sensors, or water trough level sensors are also some of equipment that could simplify ranch manager or ranch management in these extensive rangeland systems. Just for an example, on the short video on the left, it is showing cow locations inside a pasture at the Honara experimental range, and a pairing of the calf proximity loggers when the dots turn into red. This demonstration just shows how precision agriculture can be used in locating cows, but also tracking cow-calf contacts and seeing if there is a need to intervene when a calf has not established contacts with its mother. The easiest application of precision agriculture is also going to be on data management. For instance, knowing for sure which cow is in which pasture, or just as said earlier, with the proximity logger capability in detecting the pedigree of a dam or spring pairing. Now that I have shared all the complexity associated with precision agriculture, but also have shown its applicability in the application setting, I'd like to conclude my presentation by looking at the future of precision ranching. Under adoption consideration, I have listed cost to benefit ratio, total investment cost or time and effort required, simplicity and easy of use or local technical support. A questionnaire given to 36 ranchers and feeders from Southwest United States showed that 31% would consider animal sensors, whereas 50% would consider water level sensors with 3% already using it, and 42% would consider rainfall sensors with 8% already using it. These are very promising results. Under the precision technology potential, it has a potential of reducing rancher monitoring cost, reduce the environmental footprint of monitoring, free up ranchers' time, improve animal welfare, respond to changing consumer preference with traceability, and in some areas, it could also be used to improve grazing management. A case study that was also reported by Spiegel 2020 showed that at the Honara experimental range, which is approximately 780 kilometers squared, by just using the water level sensors, we're roughly able to save 388 to 400 hours of driving time, which was equivalent to 700 to 900 gallons of fuel, translating to almost $7,800 to $10,000 in annual cost savings, and about 6.6 to 8.5 metric tons of avoided carbon dioxide emission. These are just a small example of how precision agriculture can enable ranchers in the Southwest who are dealing with very thin margin of return of investments. And with that, I'd like to say thank you. And I have the Southwest Beef website linked. And if you have any questions, I have also left my email at shelemia@nmsu.edu. And thank you for listening to this presentation all the way to the end.